We have already seen how to work with mixed effect model, and the general form of the mixed effects model that we have seen is this: y equal to x beta plus zg plus epsilon, with suitable assumptions on the random parts g and epsilon. I have also hinted that it is possible to have a model in this form which is of no practical value, which has no real life interpretation. One example that I have mentioned is this: yi is equal to alpha naught plus alpha 1 xi a2 xi squared then alpha 3 xi cubed. That is, I am fitting a cubic polynomial, but out of blue I am just making a2 a random coefficient. It is impossible to come up with any real life situation where this will be the natural model. However, it is still in that form. So anything that is of this form need not be meaningful. In order to avoid creating meaningless models, we have given one way, and that was think in terms of the box diagram. Look at the inputs, identify the input which is not going to be important, or the particular levels of which are not going to be important in future. Consider that as the random input. Then if that involves subscript say j, everything involving that subscript j, all the coefficients with that subscript, will be considered as random effect coefficient. That is how R also wants you to think. So you can think of all the models that we can couch in this particular form as one set. So this big set, it's like a Venn diagram. This set is the set of all models of this form, and all the models that come from this particular way of thinking is a subset of that. It's a rather small subset. So there are other things out here, many of which are just meaningless. However, there are certain types of models which are somewhere here. Those are actually meaningful. Now we are going to discuss three such types of random effects model or mixed effects models which are not of this type outside this set, however, which are of this type, and still these are meaningful models. The first type is where we have a model like this. I have got mu plus alpha I plus beta j plus ai plus epsilon ij. The striking part here is that I have the input denoted by I as the fixed effect as well as the random effect. So this might look surprising. How can the same thing be both fixed and random simultaneously? Actually, this is a very simple trick to incorporate non-zero mean. So when we say that AI is a random effect, we have some such assumption in mind. AI follows normal 0 sigma a square. Now by the theory of linear mixed effects model, we always make the mean 0. But it may happen that you actually expect this mean to be non-zero. So AI will have some non-zero mean which you do not know. So the mean of A1 need not be same as mean of A2. That mean is just written separately out here. So this is basically same as the model. You forget about alpha I here and you put the alpha I here. So you are having AI's random effect, normal, mean some unknown alpha I and variance of sigma a square. But since standard softwares will always put this assumption, it has to be 0, you just make that into a separate fixed effect. So that is why you sometimes see in a linear mixed effects model, the same thing is listed both in fixed as well as in random. Now the effect here is that this is the design matrix X, mu's the alpha columns and the beta columns. So I am assuming I goes from 1 to 2 and j goes from 1 to 3. Then the z, which is just ai, is nothing but the two columns of x devoted to the alpha i's. So z is actually a submatrix of x. This is actually a very common situation where all the columns of z also occur as columns in x whenever you need non-zero means of the random effects. Now if you want to express this model in R using the function LME, then here is the syntax. You write fixed equal to y tilde I plus j. I am using the same name for both the variable as well as the subscript. I plus j, 1 is implied, and the random is tilde 1 given I. That is for the alpha, for the ai term. Sometimes you see a model of this form: yijk mu plus alpha I plus beta j plus gij plus epsilon ijk. Here the interesting fact is that I and j, both of them are considered as fixed effects, yet the interaction term is considered random. So why is that possible? Now the reason why people will sometimes use such a model where lower order terms are fixed but their higher order terms are considered random is to come out of a problem that sometimes occurs in real life. It is like this: that suppose you have got certain machines and you want to study how they behave, and these machines operate under two types of conditions. One is their internal settings, so I will call it settings, and I have got, say, environment. As an example, you can think of this. Suppose these are washing machines and the setting will be the speed at which it will turn and the number of turns it will make, or whether it is moving in the same direction or will keep on alternating directions and things like that. An environment might be the type of laundry that you are trying to clean, the detergent that you are using, and all these things. Now suppose that there are, say, 10 settings, 10 possible values of the settings, and there are, say, to fix up ideas, there are 8 possible environments that you can have. So there are 80 possible combinations. If you really want to keep interaction effect in mind, then there are 80 possible combinations, and that is a huge number. And suppose you also want to allow replication, say k, you want to keep 1, 2, 3. So k will go from 1 to 3. For each combination, you want to do it 3 times. So that will require 80 times 3, 240 runs of the machine. Now, if the machine is something more expensive than just a washing machine, in that case, you may not be able to afford this many different combinations. In that case, what you do is this: you make this grid. So you have this 10 by 8 thing. So I have got 10 possible settings and 8 possible environments. Instead of looking at all possible combinations, you pick some of them at random. And then you will carry out this experiment with k equal to 1, 2, 3 here. So you will take this combination and run the machines in this particular combination 3 times. Similarly here, here and here. These 4 are just chosen randomly out of all the 80 things. Then you can still use this model. You cannot, of course, use this model because some of the ij combinations have not even occurred. You can still use this model under the assumption that Gij's all behave more or less similarly. They come from some identical populations, 0, sigma, g squared, of which you have got 4 samples. Well, from 4 samples, you can have some idea about sigma g square. You cannot estimate all the gamma ij's. That is impossible. but you can have an idea about how much variation you can expect because of different setting environment combinations. So in such a situation, there is just no other way out, because interaction cannot be ignored, so you cannot work with this. You cannot afford to have all the combinations, so you cannot work with this. So either you have to abandon the entire study, or you can work with this mixed effects model. So this is often a lifesaver in real life. The third type of linear mixed effects model that we are going to discuss actually is part of a very big class of model which are called hierarchical linear mixed models, or HLMM, or multi-level models. Now let me illustrate this with an example. We have already seen examples of this type where we are studying the effect of technology, teaching technology, on performance of students. So the teaching technology could be whether I am using just a board, or I am using, say, PowerPoint, or I am using a smart classroom, etc., or I am teaching using some online mode. So these are the different teaching technologies. This is a factor. Those are the levels. And the students, and I've seen the result. Now naturally, school will also play an important role. So I have such a model. And suppose I am interested in those particular schools. So it is not that I have just picked up some random school. So I am interested in the schools. So in that case, I will have a fixed effects model like this: mu plus alpha I plus beta j plus epsilon I j k. Suppose I am considering these as I and these as j. So I of course have the random input. Now let us understand this particular school. Now when I say the school has an influence, so this beta j is the influence of the school. Now the school is actually consisting of lots of different things. For example, what is the average income of the parents there? What is the total area? Whether the school is situated in an urban region or a rural region? What is the amount of open space in the school? All those things are part of the school. So it is quite natural that you also collect data on those things, and you have something like this. You have school, and you have inputs like area, and we can have, so it is the play area. Suppose I say play area proportion, and we may have input like medium. What is the medium of instruction? We may have things like, say, the economic status of so the average economic status of the parents of the students, and all these things gives you the sum total effect which comes here. So it is quite natural to extend it in this way. In fact, when you will collect the data, you will actually collect it in that way. So you will have a table for students. So student 1, student 2, etc. up to student n, and you have got their, so what technology they have been used and the results, etc. So you will have a student table, and then you will have a different table which is for schools. School 1, school 2, school 3, and for each school you will have various descriptions. That is why it is called a multi-level model. In the lowest level you have students, which is nested inside school, and like that. If you consider it like this, then isn't this box basically similar to this box? Here the output is somewhat abstract. Output is this beta j. So this beta coefficient is the output. Unlike here where result is a very concrete object, but beta is just a similarly measurable quantity. Beta is the effect of a school on the result of its students. Quite abstract sounding thing, but it's a quantity. And that is the output of play area, proportion, medium, economic status, blah blah blah. Now, do you expect that all these things completely determine beta? So you can have a precise mathematical function describing beta? Of course not. The reason why we had a random error input was because I cannot model this exactly mathematically in terms of the inputs. The same thing works here also, so we must have a random error here also. So you see, the beta that I have is actually result of certain things that are known plus certain thing that is random. So this beta must be considered to be a random quantity. So this will be basically Bj. However, in this case, I am not going to put a condition like Bj normal 0 blah blah. Instead, I will have the second level of equation. Bj is equal to, again, I will have another linear model which describes this in terms of these inputs, and it will have its own epsilon, it will have its own eta j. So this is the random error there. And the thing can go on and on. The school is situated in a city, so you will have some database for that cities. In this way, you have a multi-level model and you get various random effects because they are the result of the earlier levels or the higher levels. These are percolating down to the lowest level. And everything that comes through the higher level also is influenced by the random errors in those levels. As a result, they are actually all random. Now, if you want to write it in this way, R makes it particularly easy to do that. So in this case, what you will do is you have school and you have student. So you will write things like, so you have take here. So I have student and I have school. So that is one random effect. So you will write down all the models in the random part. So in this particular example, I have only one level. So I will just write one thing. Random list school equal to, then you will write tilde and whatever stuff you have for this input. If there is something else, then you will list that also. Suppose this is nested inside city. So before school, you will write city equal to tilde blah blah. Under that, school equal to tilde blah blah. And such a data set is called a multi-level data set. Typically, it will be stored in a database as different tables. But when you run R on that, you have to combine everything to produce one big table, which means student. Then for that school, all the information of that school will be repeated. And like that, finally, you will run a model like this, which will tell that city is the highest level, school is the next highest level, and finally the student, that is the lowermost level. Now, in our course, we shall not go into any greater details about this thing because this will take us far afield. But I just wanted you to have a basic idea about how multi-level models work. If you want to read more about it, in that case, it's a good idea to read that book by Pinheiro and Bates, especially the section on split plot design, which is one very common example of multi-level modeling, split plot design. In the next semester, you are going to learn about split plot design, and many students have great problem understanding what this is and they end up cramming it. So I would suggest that before that class or when you are suffering in that class, you have no clue where to read split plot design from. Remember that this is a very good reference for learning about split plot design.